in the last class. So we started with a regression problem, which means that we are given some data. We took an example that, okay, we have got temperatures, let's say in a day, in a particular day, I have got temperatures at 5 different times, and I want to predict temperature at any time of that particular day, right? We took that example. So let us say this is the my space, like this is time in that case, is the temperature. Temperature is varying during the day, and I have got just 5 points, and then I want to predict temperature at any time of the day. So I call my known temperatures by T1, and that the times as T1 x1, and then I want to estimate the temperature at any point, so that I call as y1, and I say that my y is a polynomial model. So basically my y is so here x is a scalar, y is a scalar. Very important. We'll see this more today. So my weights are all, I took a capital D order model, which means I am considering d plus 1 unknown parameters which I am optimizing. And this is what my model looks like. Y is equal to this thing. Now, just a second. Okay, so this is my model, y is equal to this thing, but I want to estimate the values of W0, W1, W2, W capital D. How do I do that? So we discussed a scenario where my W is equal to, where my number of points is equal to number of equations. So this is basically like solving n number of equations, and for d plus 1 unknown parameters. If d plus 1 is exactly equal to n, then I say that this is a and all these equations are linearly independent, then I say a unique solution is possible. But what if it is not true? What if I do not have d plus 1 equal to n? I can have d plus 1 less than n or greater than n. So in the last class we looked at one such example where we had d plus 1 less than capital N. So this was the example which we discussed. Okay, I can represent my y is the unknown thing. So this is multiple samples, like y is a vector, because I am training. This step is called training. Training means I am training for my unknown w's. I am trying to estimate my unknown w's. So sorry. So my y is my y vector is basically y1 to y5. I think I had written it before. Yeah, it's here. My y is y1 to y5, and my phi is like this. So when this row multiplies with this column, so we get this thing, which is the estimate y1. Okay. Now I can represent this equation in the form of a matrix equation to find the error. Error is the difference in my true value and my estimate. If my estimate is same as the true value, the difference is 0 and my error is 0. But if the difference is large, my error is accordingly more. So here in this case, we are using a Euclidean distance. But we have discussed before that I can use any kind of distance. Cosine similarity we discussed, Euclidean distance, or any other L1 norm, L3 norm, any kind of norm we can use. Okay, now I have formulated my error function as a function of W. Now I want to find the minimum of E with respect to W. It is quadratic equation with respect to W. So I just take a derivative and put it equal to 0, and I get a unique solution. I get a nice solution which looks like this. Since this is a quadratic form, I know this is the minimum, because just looking here I can know for large W my error is very large. So this is a minimum. And we discussed some matrix calculus in the last class. The effect of increasing data points. Now in this example we considered 5 data points, just 5 samples. If I have more samples, will my estimate improve or degrade? Yes, so I can also simulate the whole thing. So in this case I have 3 samples. Model size is 5 always on all the examples. When I have 3 points only, then my model fits the data very well, and on the training data it fits very well. On the test data it does not fit very well, because it has learned from very little training data, so it generalizes not very well to other unseen points, right? But now if I increase the number of points from 3 to 5 to 30, as I have more and more points, my generalization capability improves. It does very well on the unseen data, as you can see here. So both these graphs are just on the training data, on the test data. On the test data, my curve fits the unseen points much better than that with the smaller data. Okay, this is what we discussed in the last class. So this is also a curve which shows how by increasing the number of data points, my error is reducing. The error is very large here. Error keeps going down, and it is very small anyways for these cases as well. Okay, so having more data always helps. That is why all the machine learning companies, they are after data, right? So they say if your machine learning algorithms are like rockets, data is the fuel. Okay. So there are companies which just generate data. Okay. There are companies who have business to give you good data. So this is okay. Now I took the same model, the one which we just now derived the results for, and so if I take my D, so this is n equal to 5. Now I have fixed my data size, n equal to 5, same data, but my model size is changing. My degree of polynomial is changing. If I use only single degree, it will be a straight line with m and c, right? Constant called c, and the w1 will be the m. So I can get a straight line, so this can fit the data like this. This is the optimal value of m and c. Somebody was asking in the previous classes, how do we estimate the value of m and c? So this is your first method to estimate m and c. And it works very well. This is the optimal solution for the given case. It's a simple case, so optimal solution analytically is possible. But for more complicated models, it won't be possible. Okay. So then I increase the degree of the model. Now degree is equal to 4. It is able to fit much better, and on the training data it fits exactly. On the test data it is able to fit very well, only a few errors here and there. Now if I take a very large model, Very large model, very little data to train. What do you expect? What do you expect? Huh? Degradation or improvement? Oh, this degradation is counterintuitive. Okay, let me ask this question in this way. If you have a small, for same data, if you have a less powerful model versus if you have a more powerful model, the more powerful model should do better or worse? Better, but it is doing worse. Right? Why? Huh? Good answer. It's called overfitting. Let me show you. Oh, I don't have the plots. Okay. I don't have the plots. Okay. Okay, I don't have the plots for that. Maybe some I had put them, or maybe I don't remember where did I put them. Okay, so this is another method to reduce overfitting. How do we reduce overfitting? So we have the t is the true value, w is the phi w is the estimate value. The same error function called the least squares or squared error function, mean squared error function, and I add this term. This term is, it will penalize the size of w. So maybe I can draw a rough plot to give an intuitive understanding. So if I have, so this is my model capacity. Model capacity means number of unknown parameters, let us say. Model capacity or the learning capacity of a model. And here I have the error. So if my model capacity is too small, my error is very high, obviously. As I increase my model capacity, my training error goes down and down and down and down until it really becomes very small. If my learning algorithm is good. If learning algorithm is not good, then that is a different story. But on that unseen data, my performance will not be in this way. On the unseen data, my performance will be like this. It will come down and down for some time, but after some time it will start increasing. Why? Because if I am trying to fit the data, my model puts so much effort in fitting that data that it becomes very spiky and the weights become very large. That's why it becomes, it's not able to have generalization power. But if I introduce this term called W square, just the W square term, if I am minimizing the size of W, so I am trying to put a limit on my model capacity. Even if I have large number of unknown parameters, W's, but I'm reducing the power of each W by limiting it to a smaller magnitude, right? So in this way, I'm trying to control the model capacity. So now, if you have got this curve, what should be your operating point? What should be your optimal operating point? This point? Because here you are getting the least error? No, because this is the error on training data. And when you deploy your model, you won't see training data. You will be seeing some unseen data before. So you want to minimize over this curve. So which means this point is your optimal point. This should be your operating point. So here it is called, why performance is bad here? This is called underfitting. Your model capacity is very small and data variability is large. So it is called underfit or underfitting. And if your model capacity is too large but data variability is small, it is called overfitting. You don't want both these situations. You want an optimal situation which is somewhere in the middle. That is why you have to choose your model. So generally what we do is, we do not, this red curve is not on the test data, but what we do, we create 3 sets: training data, test data, and another set of data called the validation data, which we use for finding the best model capacity, or finding the best size of the model, and so that my performance is maximized on the validation data. So let me write it down here. So this is the validation data. Should I use that? Okay. And this is the training data. Right? I want to minimize my validation error, not the test error, sorry, not the training error. Of course, test error will be used later just for evaluation. I won't be doing any optimization on the test error, right? I won't be optimizing with my test data. That will be cheating, right? So an intuitive example could be when you are learning in the class. So there are many solved examples which we do on the board, or which we solve in the class, or which solutions are given to you to learn from. And then there is the test time, in the exam time, where you actually go and write the exam, which is once only, right? At the end of the course, or maybe twice, one in the middle also. So, but the test, you do not learn during the test. You only vomit out during the test. So, but how do you know whether you have learned or not? How will you know? The customers or the users will know in the test time only. Like if I want to know whether you have learned or not, I can know only during test time. But how will you know whether you have learned or not? So you will do some mock tests, right? Or you will solve unsolved problems at the back of the book or the reference. So that will be like validation. So you learn from the solved examples, and then you do a validation by solving unseen problems like mock tests. And then finally the test will be there, which will be just evaluated. You won't be learning from there. So that is the way we do. Validation. Okay. So this is a method which we are just seeing on the screen here. This is called ridge regression. So whenever we use W square or L2 loss, L2 regularization. Regularization means you are putting some constraints on your weights so that the model becomes better. That is called regularization. Oh, this is a mistake. It's called regularization. L2 regularization or ridge regression. So now this is my error function. How do I find the minimum? I differentiate it with respect to W, put it equal to 0, and that is my minimum. Means for this W, my error is minimum. You can solve it analytically and find this value. It's very easy. Okay. Now another kind of L2 normalization. So in this case, my error function is not a squared loss or squared error function. It is a L1 difference, L1 error function, which means I am taking L1 norm of my error, and I am using L2 normalization. And it turns out I can solve this also analytically. How? Okay, let us do it. So the derivative of E with respect to W will be equal to. So I have to differentiate this thing. So what will be the derivative of mod of x? It is or mod of f of x. It will be sine of f of x, signum or sine, not sine but sign, or signum of the f of x, and the derivative of f of x. So signum is here and the derivative is this one. So we discussed in the last class how do we take derivative of a matrix or a vector. So this is what I obtain. Plus I have these two matrices multiplying, two vectors multiplying, and I can just say twice of lambda w, the derivative of this thing. So I obtained this. Now I solve it with respect to w. W is this, but I do not know what is my lambda here. So I can use a trick. Since this is okay, I think I missed something. So this normalization, this solution is applicable if we have more number of parameters than the number of equations. So which means that my model can always learn the training set perfectly. I'm only minimizing my generalization loss, generalization error. So my t means I can always optimize my w so that phi w is equal to t. So I can, so that's the constraint I'm putting here. So consider t is equal to phi w. So in this case, my d plus 1 is greater than capital M. So I can always find t is equal to phi w. And if I substitute in this equation, I get, so substitute in this equation, I get my t is equal to phi w. W is this thing. So I get t is equal to this thing. Now I want to find the value of lambda, right? So which means 1 upon 2. Okay, from here I can get. So 1 upon 2 lambda signum of this whole thing becomes just the phi transpose inverse can go that side. Because phi transpose is a square matrix. Okay, so substituting it back in equation 1. So 1 upon 2 lambda times signum thing can be replaced with this. That is what I get. This is called the minimum norm solution. This is another way to solve, but this is applicable only when capital N is smaller than d plus 1. Okay. Now, with this equation, with this solution, if I solve, this is what I get. If my N is 5, d is equal to 2. Consider this case. When N is 5 and d is equal to 10, so I get a very nice fit. Okay. So for small values of d, performance is bad, but for large values of d, performance is much better than what I got with the least square solution. Okay. So this solution does better for large d, but worse for small d. Of course, because that assumption which we had taken is not valid here. Now, caution. I have shown this graph only for a single iteration or single run. I just took one random set of points and ran this algorithm. I have not averaged over many runs. So in a way, I am showing you only the best result. And I actually obtained many bad results also. So, okay. So, I discussed in this example, summarizing the whole thing again. So what I discussed is, if you have a large model and less data, versus if you have a smaller model or smaller capital D, but a large data, right? If I have a large data, I can use the least square solution. It works very well. But if I have small data and large model size, it gives me overfitting. It overfits very badly. This one? Yes. So in this case, good point. I didn't notice this. So the training error is very large here. think I did a mistake in plotting. Okay, training error should have been small. Okay, training error should have been small there. Okay. Now coming to yeah. So the point is that if I have a small training data and large model, I want to constrain my model in some way. So we discussed two ways to do that. One is L2 regularization or ridge regression. Basically, I apply L2 normalization on the squared error loss, and I obtain my W. Another is I apply L2 normalization on L1 norm error, and I get some analytical solution which also works very well. It's called the minimum norm solution. Then effect of changing model size, I see, okay, for a large capital D also, the model is doing better. Okay. In general, what is the concept of regularization? In general, I could have any loss function here, any error function. It need not be just least square error or least L1 norm error. It could be any loss function, but the regularization term is what is important. If I use Q equal to 1 here, which means I'm minimizing just the L1 norm of the weights, then it is called lasso, or yeah, it is called lasso. But if I minimize the squared term, W square, then it is called ridge regression. Okay, so this is a nice figure to explain the thing. So what is this term doing? So this term is minimizing a quadratic function, and this term is constraining my solution in certain way. So how is it so? So if I use an L2 norm, L2 regularization, then my W square, if you see, let us say this is the best, this circle is the best squared error which I can obtain, the first term. Consider this first term. So this blue thing corresponds to the first term, and if you look at the second term, then this orange circle represents the second term. So for the same solution for the first term, my second term will be minimized only when I take this solution. Is this point clear? If I am able to minimize my first term so that, let us say my first term is 10. Let me take some values to help understand this thing. Let us say the error here is very large. Let us say of the order of 100. The error here is of the order of 70. Error here is of the order of 40. Error here is of the order of 20, let us say. So this is the squared error, like here, T minus phi W square. So this term will be, so on every point on this curve, this thing is same, right? Any value of W if I take, any value of W I can take, my estimate is equally good or bad, right? But if you take this value, which is very large W's, your generalization error is very bad. You don't generalize very well because it's very spiky because W's are very large. You want to minimize, you want to constrain the weights of your W. So what you can do is bring your solution, means without degrading the quality or without improving the quality of your estimates, bring it down to this point. And then on the test error, on the training data, so this is on training data. On training data, the performance is same, but your W's are small now. And because of that, your generalization is better. Your test error will be smaller. So here, on this point, you will get small W's. Okay, so this is called L2 regularization. But on the other hand, if you use L1 regularization, then, so here again, this is the same thing. This is 70 something. But here you are constraining your W's, your W norm is minimized. Here your W square was minimized, but here your W 1 is minimized. The L1 norm is minimized. So which means this is essentially, it means W1 plus W2 is equal to constant. And what is this curve? W1 norm plus W2 norm is equal to constant. Essentially, this is this curve, right? Now you are constraining your solution to lie on this curve. Basically, let us say you obtained a point W here. It gives you an error of 20 on the training data, but on the test data, you know it will be giving a very bad performance because the W's are very large. You want to constrain them to have small values, so you bring them to here. So you bring, now since you are minimizing W1 norm, so it will come to this point, not to this point or any other point, right? So this is the thing. Okay, so let us say if I have my Y is equal to phi W. Okay, can you just do a visual inspection of these graphs and tell me what is the advantage of L1 over L2, or equivalently, what is the advantage of L2 over L1? They have both their pros and cons. What are those pros and cons? Can you tell me from these plots? So here you have to use your imagination, understand the meaning of W1 and W2. I have written in front of you the equation which will give you some hint. Good point. Yes. If we use L1 regularization, so in this case, if you see, my W1 is 0 and my W2 is a finite value. So my L1 normalization, my L1 regularization is constraining or is forcing some of the W's to go to 0. How does that matter? How does that matter? Model becomes smaller. Now if you look at this equation, so here you are multiplying, let us say, one vector with another vector, right? You have 1x, x square, so on, multiplied by W0, W1, so on. Now if I say that you make W1 is equal to 0, which means you made this equal to 0, what will happen? This means that your output no longer needs this thing. Your output no longer depends on x. It only depends on 1 and x square and other terms, right? It does not depend on. So basically, you can do feature selection. Feature selection means you can choose which inputs are important for you and which inputs are not important for you. For example, I give you temperature data. I want to predict temperature tomorrow, and I tell you today's humidity, today's pressure, today's, like, so many parameters, like hundreds of parameters I give you, right? And you know most of these parameters will be useless, right? If I give you some useless parameters like my age or time of the day, or time may be important, or time of today's class, means some unrelated parameters, right? So what your model will do, if you use an L1 regularization, your model will put those weights to 0, right? Because your output does not depend on them. And then you can know which features were useless and you can just throw them away. This is called feature selection. This is a very important tool in time series analysis. Time series analysis is what we just now discussed. Let us say predict the temperature tomorrow. You can find out which quantities are not important for your task. Okay. Now some extensions of the same thing. We discussed scalar x and scalar y. What if my y is multiple outputs? It's very simple. So instead of writing a vector of all the observations, now you will write a matrix of all the observations, where the first row is the first observation, second row is the second observation, and in this way you can derive the whole result, same derivation as we have seen before, but just that now you have multiple outputs. Okay. Now this is important. What about multiple inputs? Can you handle multiple inputs also? Yes, you can do that. So we use the polynomial function, but who constrains me to use a polynomial function? I can use any function. And let us say, let us take an example. For example, I can say my phi is 1, and then maybe exponential of x minus 1 whole square, then exponential of x minus 5 whole square, and in this way I can choose any number of functions. And who asks me to only use x? I can also use a vector, right? Phi could be a function of vector x, some vector x, not a scalar x. So phi can be a function of vector x instead of simply x to the power d, which was the polynomial thing. So in general, I can write for a single sample, I can say my y transpose is equal to phi of x into w. Why did I use a capital W here? It's a matrix of size I comma j, which is capital D cross ny minus 1. Is this clear? I think we discussed this point here. So my W was a matrix here. Why? Because now I want to estimate different rows of different columns here. So each column will come from different W's. Okay. So this is how I can say, I can write my in the matrix form, and this is in the element wise form. Both are important, as we'll see in derivations. Both are important. You can derive in using any representation. For multiple samples, you can write it like this. So this is the same thing. Okay, some important references now. In PRML book, section 1.1, highly recommended. Section 3.1, highly recommended. Section 1.1 is an introduction to machine learning. It deals with various concepts which we briefly covered. And then section 3.1 deals with linear regression, and matrix calculus we have already seen. Okay, so let's come to the next. Okay, so today we are going to discuss regression again. So until now we discussed analytical solutions. We discussed how you have an error function. You want to minimize the error function. So what do? You differentiate it and find the optimal value of W. And whichever value of W is optimal, you say you are able to find an exact analytical solution for that W. But what if analytical solution is not possible? If your form is so dirty that you cannot solve it exactly, what do you do then? Then you have to use approximate solutions or iterative solutions. What are iterative solutions? Okay, what are iterative solutions? So you have got EW, error of the error function, which is a function of W, and you want to find the value of W which will optimize the whole thing, right? Analytically, you can find this value for simple error functions, but if the error function is very complicated, you won't be able to find it. How do you do it? You can always use iterative solutions. How does that work? So it works like this. You start from a random W. Start from a random W. Okay, but this random should not be like a very bad random. I can take 10,000 comma minus 55,000 comma, like don't do very random thing. Find something which is random, but the general rule of thumb is it has smaller magnitude. Magnitude is small. We'll discuss more about this in the coming slides. So start from a random W. I can explain at the for the time being. I can explain it from the figure. So you have, if you take your W very far, let's say if I extend this axis somewhere here, of course your error function might be something very weird in the. If you extend it further, it could be like this, and you will never reach the optimal point, right? That is what I mean to say when I say do not take a very weird kind of W. So okay, start from a random W, and then what do? Find the slope basically, which means dou E by dou W. Let me call this as W0, random W0. 0 is not a degree; it's just just the index, and you compute it at W0. So which means you come here. At W0 you find the slope, dou E upon dou W. Now you know that you want to go in a direction which will reduce your error function. So why don't you move your W in such a way that you change your W, that your W new is equal to W old minus the slope. So which means if your slope is increasing, okay, now my slope is increasing here, so I will decrease my W so that my error decreases. So my dE upon dW is positive here, so that is why, and I want to reduce my W. So that is why if this thing is positive, the whole thing will decrease, right? So that is the idea of gradient descent. So you are descending along the gradient and you are going towards the optimal. So, and then so you update your W, and then 4 again go to step 2 until convergence. What is the meaning of convergence? How do you know it has converged? When your dou E upon dou W will become very close to 0, right? When your things will stop changing much. When your W will stop updating much. So that is the algorithm which you can derive, right? This is an iterative algorithm. How many of you remember Newton-Raphson method? So it means, okay, almost all of you have at least know this concept of iterative updates. Newton-Raphson method was a different form. As far as I know, it is used for only scalar functions, but this one is used for vector functions also, because my derivative is in the numerator, not in the denominator. Newton-Raphson method has derivative in the denominator. That's why difficult to handle. Okay, so this is the gradient descent. I can use it for any dimension of W. It could be a vector, it could be a matrix, it could be anything, any tensor. And this is the general formula. Tau is the index, iteration index. Basically, in the first iteration, you update your thing, then second iteration again update it. So that is called an iteration. So now, if I use the previous form, which was written here, this thing, if I reduce dou E upon dou W, it is possible that my step size is so large, it may go from here to here, then like it may take larger and larger step sizes and may go out of bounds. So I can use a parameter called eta to control how much I want to descend along the gradient, right? If I descend too much, I may miss the minimum and go to some other maximum. Not maximum, but some other point. But that is why if I use my eta, my step size, then I can control the learning rate or control how much I want to descend. And this is a big topic of research. What should be the optimal step size? So if you are interested to read about this, you can read papers like adaptive gradient, AdaGrad, or Adam method. So there are different methods proposed to optimize my step size based on the data. And recently, also people have been using reinforcement learning to optimize the step size. Okay. Okay. Now coming back to the topic, sequential learning. What do we do when my data is arriving in a stream? Let us say you are getting data daily or all the time. You don't want to store all the data because that will be a big overhead on you. So, but what you want to do, you just learn from the data, throw it away. Learn from the data, throw it away. In this way, you keep updating your model sequentially, which means keep updating your model so that it keeps learning from the data as it is arriving. So, if you are using previous methods, like the analytical solutions, as we discussed, there it is difficult to do this sequential learning. But iterative solutions are possible, right? You can just get the new data, compute the gradients, and then use those gradients to update your weights, throw the data away, get new data. In this way, you can learn sequentially. Okay, I think I have put this slide here. Learning rate. How to choose your learning rate. If you choose your learning rate very small, what will happen? Let us say I have got a So this is my error, and this is my W. My initial W is somewhere here. If I choose my learning rate very small, what will happen? It will take so long to reach the optimal W star, right? And it is also possible it may get stuck in this noisy bumps. It may get stuck here in the noisy bumps, right? So that is why I do not want very small step size. But if I choose a very large step size, what will happen? In one step only I will go here. In next step I may go here. And in this way I will go out of bounds and I will never converge. So that is why too large eta is also bad. Okay. Next is, I will skip this. I'll discuss it in the next class. Coming to nonlinear regression. So now we discussed I can choose any phi. My phi can be a nonlinear function of x, but my y was still a linear function of w. What if my y is a nonlinear function of w? What can I do in that case? If my y is a nonlinear function of w, let us say in this example, my y is, so here my y is sigmoid function of phi times w. This was a linear thing, but then as soon as I apply a sigmoid function, all of you remember what is a sigmoid function? It's 1 upon 1 plus e to the power minus whatever is there in the brackets. This one, and this is an element-wise sigmoid. So just take the matrix, apply it element-wise. That is it. But this is a nonlinear function, and then you're multiplying it with another w2. So tell me, my y is linear in w2 or non-linear in w2? Linear in w2. So I can estimate my w2 using the previous methods. But in terms of w1, my y is non-linear. So I cannot use the analytical solutions. Some of you can try solving it. It is, okay, I could not do it. Finding an analytical solution for this form is very difficult. So what do? We use the iterative form. I can iterate over the, I can find my error function, and then I can find the slope of the error function at each w, and I can update my w's in this way. So this is nonlinear regression. I can use gradient descent method on any kind of for any kind of regression. Okay. Now some references. This book, deep learning book, this chapter, I think this is second chapter, maybe the ML chapter. This is highly recommended. Please go through it. It will discuss various concepts which we discussed briefly here, regularization, normalization, and things like that. And then Professor Behra's book is there, which explains neural networks and how do you find optimal W for the neural network architecture that is discussed here. And then PRML chapter 5 is again neural networks. But anyways, the first reference is highly recommended for this content. Okay, thank you.